上去吧，看可不可以？看看看，不错。放慢点吧。
Okay, so we consider situations. Let I be an interval in the real area. So if I can be an infinite interval, for example, the whole real line, or the semi-infinite, okay, or finite interval. So there are lots of different kinds of intervals. So let Ci be the set of all real valued continuous functions on R. Okay, so Ci is that. Then I is a vector space. This vector addition. That okay, and scalar. The zero vector zero function defined. So the zero vector is just a zero function. Example 3, is the set of sequence. So consider the set of all infinite sequences, okay, over the real number. So x1, x2, etc. And this sequence will be denoted as R infinity. Okay, so you may think about that. Many times. You take the Cartesian product of the set of real numbers and give many times. So you get the sequence. Vector addition. Right. So vector addition is that we define x1, x2 plus y1 equal to, so we define to be x1 plus y1, etc. Alright, so this is the second scalar multiplication alpha. Okay, we define the scalar multiplication to be so a complete. So this is that for any pair of infinite sequences, the sum of these two infinite sequences is defined to be this one. So again, it's an infinite sequence. Similarly, given a real scalar and an infinite sequence, the scalar multiplication between them is defined to be that you multiply the real number alpha into every component of the sequence. So this is the definition. And so again, it is also in the R infinity. So these two algebraic operations are well defined. As I say, that you have to check whether this definition is what you have. Just like here, the sum of two continuous functions must be continuous. So this is similarly, if f of t is continuous, then alpha, a constant times a continuous function, is also continuous. So always check whether the definition is well defined. So now we have checked that this is true. Then, right, is a vector space over R. Later on, I will gradually mention where our scalars come from, and that means that for this vector space, the scalars are real numbers, because gradually I will introduce complex numbers into the arena. For zero sequence. 0, 0, 0. Okay, so it's the zero sequence. Alright, so this is the first example. The first example. Alright, L. Y. R. Yes. Middle one R. The R is the set of all functions. And R, Y. Okay. So it defines on the whole real line. Okay. And its real value such that it's finite. Set of all real value. When we say real value, means that the codomain is the set of the real number, right? And the function integral defined on R. Integral means that here, that we take an absolute value, okay? The value and integrate over the domain, because we define the function from rising to infinity. Then its integral means that this integral is finite. Okay? Otherwise, it's not equable. Integrable means that the integral is finite. For example, so consider a simple function. Right? Consider simple, just a linear function. Then, when you check, is this function integrable over R? Maybe I use on R. Maybe I just use on R. Is that true? Well, so this is what is that? 2 times 0 to infinity. Okay, because symmetry. Okay, and what's that? So this is infinity. So f of t is not integrable on R. So ft, the linear function, does not belong to this set. So this set is you know, linear function is very common, right? Very common function, but it is not integrable. Okay, it's not integrable function. Thus, f of t not belong to L1 R. Okay? So now I will select a function which is in L1R. Okay. So consider level P. Okay, so I define the exponential function. And so I check. And so this is the function is already non-negative, so fine. Okay, and the symmetry. Okay. I can write it as this integral, and so this is what this is true. So it's finite. That's Fp equal to P minus P. This P L1R. So for any function, which is integrable on the whole real line, the behavior should, the function value should decay right, to 0 when t is go to plus infinity or negative infinity, right? So it's something like bear shape. Otherwise, the function cannot be integrable. This is the general behavior. Okay, so it's just like something you can decay, should decay. It should decay something. So this is a general behavior, but could be very complicated, but I just illustrate that. So for linear function or quadratic function or any polynomial, polynomial function, for any polynomial function cannot be integrable on the whole real line. Cannot. Because they cannot decay to 0 when t goes to infinity or negative. Why do we put 1 here? Because we take the 1's power of the integral. If we take the square here, then we have there 2. But that is another story I will tell later on. So if we have power here, 2 here, the square here, then it represents energy. Why? Because if you think about the F of t is the current or the voltage, a signal represented electrical signal, right? In our department, we study electrical properties, electronics, things something like that, right? So if you have an electrical signal represented by either current or either voltage, then you know that the square of a voltage corresponding to power, the square of the current corresponding to power. And when you integrate power over time, it comes to energy. What is power? Power is the energy per second, right? The joule per second, that is the power. So when you integrate over the time, you give the joule. So that is the energy. Okay? So whenever you get the second here, the integral represents that when you observe the signal, the left hand, the total energy is finite. Okay, so you're considering all the signals which has finite energy. That is practical because in the world there is no signal which has infinite energy. Impossible. If we have something as infinite energy, we don't worry about the energy problem, right? We don't need the core. We don't need the physical core. When you burn the core, you get electricity, but you get the pollution in the air, right? We don't want pollution. We want our health. So, but where the energy come from? Well, you have to, so that in practice situation, that if we consider L2R, it means that we consider all the signals which have finite energies. So that is it represents a lot of things. So we start with the study of L1R. So L1R, something like that. Okay, and so now we check the vector addition. Right. So the vector addition L1R times L1R goes to L1R. So you have a pair of those signals. So again, you get the sum of the function. So the sum is the usual addition. Okay? And you have to check whether, so the question is FP question, you have to raise this question. So if FP and GFP are two functions in the 1R, is the sum, is their sum in the 1R. So I have to check that the integral to prove that this integral is finite. And so fortunately, we have upper bound. Since the sum of two real numbers, when you take the absolute value, it is the upper bound by. So if you take the absolute value for a sum, then it's upper bounded by the sum of their respective absolute value. Okay. So this is a truth we have. And so that because this integral is less than or equal to this integral, so the integral will have a form here. Okay, so now we have inequality. But by linearity of integral, so we have and this is finite, right? And this is finite by our assumption, because they are in L1. So the sum of two finite numbers is still finite. So this is that. So that's the answer. Yes. Okay? So the answer is yes. No problem. So we can write this assertion. When you write this assertion, you have to prove it. Okay, things become more and more difficult if you consider more complicated vector spaces. Okay. So you have that. Yeah. Second, scalar multiplication. So another question. Raise up. Right. So we have the question. So now we have to check that this integral is finite. And but this is here. So we can check out the x value of alpha. And so that this is a finite number. A finite number times a finite number is also finite, of course. So the answer is yes. Okay, and so now we have. So this is well defined. Right. So once we have done that, because the other axioms, the same axioms for the addition of two functions and scale multiplication between the scalar and the function will be the same as before, right? We already done that. So that the conclusion is that so that and 1R plus a vector space over R. Okay. Any questions? Okay, two more examples. Right, so this A be an n times a matrix over R. Means that the entries of the matrix are all real numbers. Or that's fine. Maybe I just not mention the type of the scalars. Let's say matrix. Okay. Okay, I'm in my mind, but I think that the kernel, okay, is a vector space. Okay, so first of all, vector addition. Right. And so vector addition so if we have x, y, we have go to the vector addition, as usual, as the vector addition we have. But the thing is that, the vector addition is a function from this Cartesian product to kernel A. So the codomain is kernel A. So you have to make sure, even though x and y are taken from kernel A, the question is, again, it's the sum of x and y in kernel A. So we raise up the question again. All right. So to check that, we have to compute this product. AX1, we check that. So AX plus AY. So we know that the R, this is the in Rm, so that in Rm we have vector addition. And so this is 0 plus 0. Okay? Because x and y are in kernel of A. So Ax is 0, Ay is 0, and the sum is 0. That's x plus y. It's in kernel of A. And your answer is yes. Because if the answer is not yes, then you got trouble. The vector addition you define is not well defined. Okay, so you have to modify your definition in some way. Scalar multiplication. So that alpha x goes to alpha x. Right? Oh, wait. And now after answer the question, now we can put here. Alright, so another question. It's alpha x. Internal A is x internal A. Right, so I have to check this product. Okay, and okay, so it's done. So that's and the answer is yes. And so we can write. Okay. So after checking we call them our closure properties. So note that most cases in about closure property. So we say that we have proved that once you define the vector addition, now you should have the closure property. Means that the sum of these two vectors in your definition should be in the set. That is called a closure, not open out closure in your domain. So this is the set, right? The scale multiplication. By your definition, you have to make sure that the result, this value should be set by the closure property. Okay, so this is remember the kernel of A is also called the null space of A. And the space, the word space comes from that the kernel is a vector space. So we use this. And it's called null because that when you apply the product, get the zero vector. So A times x becomes 0. So let X be a subset of Rn. Consider the span of, okay? So we consider span of X. We want to prove that the span of S is a vector space. So first of all, we define vector addition. We have span of span. Alright, and so we have for U, V goes to U plus V. So the addition is the ordinary vector addition. But you have to check that the sum of two vectors from the span of X is also in the span of X. So we have to check that. Alright, so claim U plus V span. Okay? So claim. And the proof is that since U, V is in the span, there are one, two, up to M. 1, 2, up to K, alpha 1, up to alpha M, beta alpha. In X, okay, and alpha 1, alpha 2, up to alpha M, beta 1, beta 2, up to beta K, or such that U equal to alpha 1 U1 plus 2 U2 plus 2 plus alpha M UM. Because when we say U is in the span of X, we mean that U is a linear combination of elements or of vectors in X. So if we have, say we have M vectors in X, and we have M scalars, so that U is such a linear combination. And V is also VK. And also you can find the K vectors in S and the K scalars, right? Such as the vector V is a linear combination of V1 up to Q. Okay? And this is from here. So now we write down the sum. So when we write down the sum, alpha 1 U1 plus alpha 2 U2 plus plus beta 1 divide. So now it's a linear combination of vectors. So a linear combination S. Okay, so that is in Spain. Of course, that maybe some of the VI is the same as UJs, right? They may, but anyway, there should be a linear combination of vectors in this in general. Right? So that is it. Okay, so we prove that, and then we can write down. And scalar multiplication. Okay. So alpha as usual, right? And for the claim. Again, we have to prove. So since U is in the span, U equal to alpha 1 U, maybe I use beta this time. 1 plus beta 2, 2 plus beta m. For some U1, U2 up to U n in the S. So for some vectors in S and alpha 1, beta 1, beta 2, etc. up to beta n in R. Right? So we have that. And alpha U comes so it's a linear combination of vectors in S. So first, this is in span. Right. So what we have done, also, real vector is in span S. Things. How do you know the span S is a zero vector? Because 0 is 0 times U for any U x. So you can select any vector in S, right? And you put the scale multiplication 0 Q, then it must be 0. So it's a linear combination of U, right? So of course, so 0 is in that. Okay. And minus u is in Spain. Okay. And the existence of the additive inverse, you have to check that, and also you have to check the and you spend then minus u is also in spend of. I think this is very easy to prove, right? It's because that here, if we put alpha minus 1, we get minus 1 u. So this is from the scale, the causal property of scalar multiplication. So you have additive inverse, you have 0 elements. Okay. So and the other things like commutativity, associativity, distributive laws, and all those things that we can have. So we conclude that span is a vector space. Okay. Any questions? Not definition. Let V be our vector space. R a subset W of V is called a subspace of V if W is itself a vector space. Example. For any m times n matrix, kernel of A is a subset of Rn, sorry. Since we just proved that kernel of A is a vector space. Okay. From R, kernel of A is a subspace of Rn. Because Rn itself is a vector space already, you know that. So kernel A, so that for any m times n matrix, then the kernel of A is a subspace of Rn. Another example. Consider a subset S of Rn then span of X is a subset of Rn. Okay? Since span of X is just prove a vector space itself, span of X is a subspace example Pn is a subspace of P. Right? We define P is the vector space of all polynomials. And we define Pn is the vector space of all polynomials of degree less than or equal to n. So Pn is a subset of P. You know that. But Pn itself is a vector space. So Pn is a subspace of Alright? So we have that situation. Alright, let's take 5 minutes break. So we define independent subset. So suppose we have a vector space V, and S is just a subset. Then we call this subset linearly dependent. If we can find some vectors in S, and this vectors has a non-trivial relation, means that the coefficient C1, C2, Cn, not all zeros. Yeah. So if this is, we can establish a non-trivial relation like this one. Okay, linear relation. Okay, a non-trivial linear relation. Then we call S linear dependency. The set S is linearly independent if no such non-trivial linear relation exists. Linear relations. From the definition, it seems that to decide whether a set, a subset of a vector space to be linearly dependent, it's just to find a non-trivial linear relation in set. Okay, so you seem like just find a non-trivial linear relation. If you find one, then you are certain that this subset is linearly dependent. But to decide a set to be linearly independent seems that you have to consider all possible linear relations and say that all the linear relations should be trivial. Okay, so I give a remark. A subset of a vector space is linearly independent if only for any linear relation in S, i.e. C1 and 1 right? So for any linear relation in S where in 1 M in S and C1 in R, we must C1 equals C2 equals Cm equals Z. So this shows that how to prove a subset is of a vector space V to be linearly independent. To prove that, you have to prove that you can establish an arbitrary linear relation in S. Okay, so you start from an arbitrary linear relation so that U1, U2, and Um can be arbitrary vector in S. And C1, C2 up to Cm, arbitrary real numbers. Then starting from here, you have to prove, to show that all the coefficients must be 0. If this is the case, then the set S is linearly independent. Because it's impossible for you to find a non-trivial linear relation. Okay, it's impossible. Any questions? Linearly independent for a subset has an important implication. Here. Let X be a linearly independent subset of a vector space. Now each vector U in the span of S. Okay? Is a unique representation as a linear combination of vectors. Let me show you a counterexample before I give a proof of the theorem. So, example. X right? So X consists of 3 vectors, right? Now X is a linearly dependent subset of R2. Since 1 minus 1 plus 0, 1 minus 1, 0 equal to 0, 0. Okay. So I find a non-trivial linear relation on these 3 elements. Okay, so now so I find that for example 2 and the minus 2. Okay, the vector is 2, 1, 0 plus minus 2, 0, 1. Okay, so that is in the span of S, of course, because it's a linear combination of the first 2 elements. But I can write another way. So it can be read as a linear combination of a single vector in S. So the same vector in the span of X has 2 different representations. So the representation as linear combination of vectors is not unique. So that's the representation of 1, 2 and minus 2 as a linear combination okay? So the representation of 2 minus 2 as a linear combination of vectors in X is not unique. Not unique. So the reason is that let's say it's linearly dependent. The theorem says that once you know the set S is a linearly independent set, then this situation will not happen. Will not happen. Okay? So if we know a vector is in the span, then this vector, when you represent as a linear combination of elements, this representation should be the only one, no others. Okay? Any questions about the statement of the theorem from the example? Any questions? Before I give a proof. Actually, I can find a third representation. Actually, there are many. Why? To solve it, you can solve the possible. When you find that you have many solutions, the coefficients, by using the law operations, we have already know how to solve it. Okay, so the proof of the theorem. Right, so we will prove that. All right, so assume. So I'll prove this. So assume that U is in the span of X such that U has two representations. So we have A1, U1 plus A2, U2 plus A and AN and UN. Also, we have B1 for an element in the span, and we have two representations. Where U1 up to UN, U1 up to AN, and N, sorry, are in S, okay, and A1 up to AN, B1 up to BN. Okay. And we have to prove that so they must be equal. Now, without of generality, right? We assume that okay, sorry. So we let one. Okay. Sorry. Without loss of generality. Without loss of generality. Okay. Later on, when you see LOS means without loss of generality, we assume that U un minus I equal to vi for I to k. Because that some of the ui are the same as the vj, and so I just manipulate. I think for those they are the same, right? I just put them in the tail here and in the front of the linear combination. So I will say un minus I equal to say. Yeah. Okay, so that's fine. So I have one plus one. Okay. And minus I plus one. Okay. With R less than equal to the minimum of n and m. So we have n terms here, and here we have m terms, and we let them the same. Okay. So for R vectors. So any questions? For example, if R equal to 1, that means that an is equal to that means that un is equal to v1, right? If R equal to 1, only one common, so un is equal to v1. But if we have two vectors in common, then un minus 1 equal to v1 and un equal to v2, etc. Is that okay? So I just so we assume that and which are common vectors in the two lists. One, two, you say n minus r minus 1 plus 1. N minus r plus 1 u n minus r n and oh, not maybe I have to modify. I want this one. VR. So I want un equal to r. How can I do so? Because the match is like I want, you understand, right? So I have to modify my index. R goes to n. So when r goes to n, r goes to n. And 1 goes to so I should have n minus r plus 1 n minus r. Now I'm matched, right? Yes, n minus r to 1. Yes. Which one? You, oh yeah, yes, thank you. Because my brain is worrying about how to make the index. Okay. Now, my purpose is to match. When these two lists have common vectors, I want them to be like, it could be expressed in this way, but they are the same. But in this part and this part, they are different. Now, okay? Because I can always do so, right? If they have the common vectors in these two lists. So this is my purpose. Because that expression can ease my proof. So I have to do this kind of arrangement. So, any questions? Yes, please.
为什么那个在 W 给了 OG 的时候，就不要直接设 UI 等于 BI 就好了，就不用可以这样设吗？
No, because I don't know, right? Because this is arbitrary. Because I say that I have two possible representations. If I consider arbitrary representations, then I don't know. The terms in this linear combination may be different to the number of terms in these linear combinations.
对对，所以说在那个 W 给了 OG 的时候，就把它说 UI UE 就是 VB。
Oh yeah, this is one of the arrangement. Yeah, that's clever.
Oh.
That is clever. I know. Good. Maybe I follow your idea.
Okay.
Alright?
Yeah,
Yeah, that's true. That's true. But okay, this is my choice. Maybe sometimes I'm a complicated person, not a simple person. But your idea is a good idea. I follow your idea. That's good. Better than me. Okay, so let me. Can I rest? Allow me to do this. Good. Okay, this one. A1, U1 plus A2, U2 plus AR, UR. Now, but the coefficient you have to change because maybe it's different. Alright, now you have A, R plus 1, and now we change to B. Alright, so B1 plus A, N. Alright, so B is how many? N minus R. Yeah. Okay. Now we have B plus 1, and now I use W. So W1 plus B and M. And so W, this is M minus R. Okay, this is your plan, right? Do I follow you?
我就是你前面假设一样，然后在 follow general velocity 的时候，再说限定就是 UI 等于 BI 就好了，可以这样吗？就是原本
No, because I just say because I have to for one representation, for the first representation I have to pick up n elements in S, right, to form a linear combination. And to here I have to pick up m vectors in S to form a linear combination. And this list maybe have some vector in common, right? So I put all the common vectors in front of the expression. That's your good idea. Okay. So I put U1 here, U2, U2. So they have common. But V1 up to Vn minus R, W1 up to Wn minus R are all different. So I have to say where U1 up to UR, V1 up to Vn minus R, sub 1 up to W n minus R are different vectors in S, right? So now I have to say so. They are all different. Okay, and A1 up to AN, B1 up to BM are. Okay, so it's better because shorter, right? Shorter is better. So the plan here. Thank you for your suggestion. Now this is our plan. So okay, up to now. Any better idea than this one? I will catch you as fast as I can. So please let me know. Okay? Alright, so I think that is as simple as possible. I mean, not as simple as possible, but simple enough for us to follow. So now I have that. Okay, so 0, U minus U. I do the subtraction. So I do the subtraction, then I have A1 minus B1, U1, A2 minus B2, U2, plus AR minus BR, UR. Okay? Plus AR plus 1 V1, AN, Vn minus R. Okay? Minus BR plus 1, W1, minus Bm, W, n minus R. So now I have a linear relation, right? So which is a linear relation alright? So it's a linear relation in S and must be trivial. Because I say S is linearly independent, right? Since S is linearly independent. Okay? Alright, so such a linear relation should be trivial, means that all the coefficients must be 0. Thus, we must have A1 equal to 0, AR minus BR equal to 0, and A R plus 1, AN equal to 0, B R plus 1, BM. And so this implies that A1 equal to B1, AR equal to BR. So these two expressions must be the same. Because what? They are all zeros, so you can ignore them. And the coefficient must be the same. So there are no other choice. So we start with two representations, arbitrary, and prove that they are the same. So that's the two representations given above are same. Okay? So conclude that. The representation the theorem is proved. Okay, so it's shorter. Okay, so we get a shorter proof because we have a nice arrangement of the expression. Any questions? So for a set to be linearly independent, it is a very strong property of that set. Very, very strong. Okay. And so we have this theorem. So the representation is neat. I consider this theorem is the most important theorem in this section. Any questions? Okay, the other theorems they are actually simple, so I don't want to mention. I want you to read through them. Okay. Okay, so let X be S be a subset of n vectors in a vector space. Alright, so now I just look at a subset, and this subset consists of n vectors, only n vectors. Then every set of more than n vectors in span of must be linearly dependent. So this theorem has a usage. Suppose you want from a vector space, right? You want to select, say you want to select 5 vectors to form a set, and you want them this set of 5 vectors to be linearly dependent. This is your purpose. You want a subset which is linearly dependent. Okay, you want them dependent. 5, right? 5. Then you can select with 4, for example, just 4, or just 2 anyway. You like it. You can select 2 or 3 or 4 anyway. For example, you take 3 vectors from V. Okay, so you take 3 vectors from V. right? And then consider the span of this set. And from this, the span of the three vectors, the set of three vectors, you select 5. Okay, you select 5 vectors from there. Then these 5 vectors form a set which is linearly dependent. Okay, so it's very easy, right? This experiment is very simple. At first, you pick up. So for example, right? So in say in Rn, we select a subset, alright, as probably I say the subset is of three vectors in Rn. Then any 4 vectors in the span of S. You should select 4 vectors from the span S because the subset S has only 3 vectors. So it's impossible to select 4 vectors from a set of 3 vectors. I mean different vectors, 4 different vectors. Possible, right? But you can select 4 different vectors from the span of this. Okay, because you have a lot of choices. So you can select. Then any 4 vectors in X form a subset, form a set. Alright? So any 4 vectors form a set which is linearly dependent. Okay? So it's very I mean, there is fairly no restrictions, right? If you see just so, if you want to have a set consists of 4 vectors to be linearly dependent, then you just select 3, and then form the span, and from the span of the set of 3 vectors, you find 4. Then this 4 vectors will form a set which is linearly dependent. So that is the idea of the theorem. Any questions? And the proof, it is something like this, that alright, so now the set has n vectors, right? Has n vectors. So select m greater than n. Okay, so we have m. We want to select m vectors from the span of S. Okay. And the U1, U2 up to Um in the span. Okay, in the span of S. Alright, and we have to prove that we can find, to prove that we show that U1, U2 up to Un is linearly dependent. We will find non-trivial. We will find a non-trivial linear relation Right, so the linear relation is that A1 1 plus A2 okay. Cool. With A1 up to AM, not all. So this is our purpose, because we want to show that this M vector form a set which is linear dependent. So we have to find it. Okay. Now, since UI is in this chain of S. Okay? And, okay, so let S equal to U1 equal up to Vn. Okay, because S has n factors. Then U1 equal to A11 V1 plus A12 A1 n Vn up to n n1 1 plus an2 into plus ann. Because they are in the span of S, so there must be a linear combination. Right? So that's the sum. So we want to show the sum is that I from 1 to m. Oh, A. I like A, but you will get some confusion, so I change B. Okay. So the zero, we want to find a non-linear relationship, right? So we have A1 and the U so we have AI, and this is AI, and the summation j from 1 to n, and each UI is B, ij, and bj, right? So the sum, so we exchange the j from 1 to n, and the summation of I from 0 to m, and so we have B, ij, and A. So I, and 3j. Now, so this is and this is now a very good okay. So that the expressions, the summation here, because what we want is that all the A want to find not all zeros. So we want to find AI is not all zeros such that this becomes 0. Okay, this is our purpose, right? And B1 they are known, but the AI are known. So we can think that and so that we try to find A1 up to AM such that the summation equal to 0 for all J to N. So if we can find AI such that the parenthesis is 0, then of course this is satisfied automatically, right? So if this is 0, then 0. This is what we want already. Alright, so we try to find not all 0. I have to say not all 0s. Such that, okay? So we want. Now this is the homogeneous linear systems. So we find that we have M so here it's A1, A2 up to AM. And so for J, so B1, 1, B2, 1 up to B and 1. Okay? And the B 1, 2, B2, 2 up to B and 2. Up to B 1N, B2N up to B and N. Okay? How many rows do we have? We have n rows. How many columns we have? We have n columns. So we want to know the kernels. Now, because n is less than m, and the rank of the coefficient matrix right would be less than equal to n, because the pivot here, every row can have at most one pivot, right? And we have only n rows, so the number of pivots should be less than or equal to n. All right. So they are at least m minus n columns without a pivot. Okay. So now they are so that A1, A2 up to AM. Now some columns has no pivot, and for those columns the corresponding are none. So So there are at least m minus n unknowns. Yeah, at least out of unknowns. And 1 and 2 up to n can be selected as free value. Okay? So we have at least one free variables. That's we have non-trivial solutions for A1, A2, okay, and we have that. So actually, we find out a non-trivial solutions means that not all zeros, such that this is satisfied. So this shows that U1, U2 up to M. M is linearly dependent. Okay. Yeah. Sorry, it takes a little bit longer than I expect. Before we leave the room, because I have a request from one of you, says that the quiz time of 40 minutes may not be enough for you to answer all the questions. So I suppose that the quiz time should be from 11:20 to 12:10. Is that okay if I extend 10 minutes for you? So if anyone objects to this proposal, please raise your hands. Okay, if not, then next week our quiz time will begin at 11:20 and up to 12:10. And to see if 15 minutes will be enough for you to answer all the quiz problems. Okay? Right. So I'll see you next week.